Hello, everyone. My name is Byron Siebold, Global Account Manager, Optics, North America for Mahr. I'd like to thank you for joining Mahr and Spectrum Scientific's joint webinar, The Not So Mysterious Art of Freeform Manufacturing and Metrology. However, prior to going into the technical presentations, I'd like to present our speakers today. Mr. David Cook is the General Manager at Spectrum Scientific Incorporated in Irvine, California. Prior to joining SSI in 2004, he was an engineering manager responsible for diffractive and aspherical optics manufacturing at the West Coast Optics Division of PerkinElmer. He earned his Bachelor of Science degree in Optical Engineering in 1994 and has also worked at Physical Optics Corporation and Northrop Electronic Systems Division. Our second speaker today, since 2007, Mr. Merten Kuna, now an applications engineer for optical systems in Mahr GmbH, has been dedicated to the study of optics and photonics. After obtaining his Master's of Engineering degree in 2012, Mr. Kuna provided his expertise as a sales and applications engineer in confocal microscopy at Convavis GmbH, a German metrology company. Currently, he is responsible for supporting Mahr's white light interferometry and freeform morphometry products. So without further ado, I'd like to hand it over to Mr. David Cook to start the presentation on the not so mysterious art of freeform manufacturing and metrology. Thank you very much.
Thank you, Byron, and thanks for hosting this event. Freeform optics are indeed a revolutionary technology. Customers are seeing tremendous improvements in their system performance, and we like to share what we've learned. First, I have a few slides about Spectrum Scientific. We here at Spectrum Scientific have been manufacturing replicated optics using nanoimprint technology for nearly 15 years here at our facility in Irvine, California. We also produce aspheric imaging mirrors in a clean room manufacturing environment. We also operate a space-qualified, silicone-free clean room where we make ultra-low stray light, high-efficiency holographic gratings. Our products include freeform mirrors, spherical and aspheric mirrors, blazed holographic diffraction gratings, both plane and concave, and holoretroreflectors used in FTIR instruments, and also they're used for laser tracking. We also have a range of miniature UV spectrometers and spectrometer components, which we supply into a variety of markets throughout the world. Our freeform mirrors are manufactured using an optical transfer process that allows us to produce a high-fidelity, high-specification freeform mirrors in OEM volumes at a fraction of the price of producing traditional freeform optics. Spectrum Scientific is currently delivering hundreds of freeforms each week using this process. I'd like to touch on the fourth bullet on the slide. It says surface figure down to lambda over 10. People get pretty excited when they see that lambda over 10 spec, and it is quite a feat and quite a great achievement for a replicated optic to even do that. But not all optics will do that. It depends on size and the complexity of the surface shape. We are providing lambda over 14 freeform optics right now. That's, by the way, that's peak to valley when I speak of these wavefronts. So we're providing lambda over 14 freeforms in production right now, and we've been doing lambda over 10 A-spheres for many years. But again, it'll always depend on the size and complexity of the optic, whether that's achievable. All right, enough about Spectrum Scientific. Let's get a few definitions underway. So according to the ISO standard, any surface that has no translational or rotational symmetry about the axes normal to the average plane is a freeform. So we've got three images on the screen, and the images on the two images on the left are clearly symmetric, but they're off axis. So that fits the definition of a freeform optic because of that off axis nature. So some of us kind of take exception to this definition, and that's because the rotational symmetry of any conic section leads to conventional manufacturing methods and also allows conventional interferometric test methods, whereas a modern freeform optic does not allow for this. You can't use first principle interferometric methods to test freeform optics. That image on the far right is also, it's closer to actually the equation is closer to being akin to a freeform equation if it's modified a bit. So yeah, there's a lot of trying to define it. There's a lot of people trying to narrow it down, but that's my best explanation. And also regarding these shapes and these images, these are kind of radical looking shapes, but a freeform surface can be varied by only a few fringes of departure and really help the application tremendously. Quite often, especially for imaging applications, just a few microns of departure will have a significant impact and will contribute to improved system performance. Back to the equations a bit. In our practice, we see several surface equations, many different ones coming from customers trying to describe the freeform surface. The generalized A-sphere equation that's been modified to either polar or Cartesian forms. Some folks are trying to use Zernike polynomials to describe the surface, and more recently we've learned of an implicit polynomial method that appears to be quite flexible and accurate. However, there's no recognized standard at this time, so the manufacturer has to do their best to interpret the surface that they're provided. And that's why what we've done is when we receive the surface equation, we produce a SAG table and then ask the customer to verify it so that we all agree on the final surface shape. In doing this, I've seen where the sign convention was wrong and the shape was inverted. And I've also seen where the coordinates were rotated by 180 degrees, in essence flipping the part over. But you think that wouldn't be a big deal because you just rotate the part 180 degrees and use it. But unfortunately, that meant all the fiducials were off by 180 degrees as well. So it's really important to verify with your customer that all the expectations are there and we're looking at the same part. So now that we've defined a freeform optic, let's give a brief rundown on the history. The concept of freeforms are nothing new. They've been discussed for a long time. Commercial manufacturing really didn't start until the 70s. And boy, back then they were called hand-figured optics back then. Let me see, where was I? And although a lot of the benefits of freeform optics were well understood, the cost and complexity of manufacturing meant that it wasn't until fairly recently that they've started to enter mainstream usage. The enabling technologies were developed in the 80s and 90s when deterministic manufacturing processes came of age. Consistency of CNC machining, single-point diamond turning, deterministic micro-grinding, magneto-rheological finishing, these technologies all paved the way for this next wave of optical precision. However, even by the late 1990s, early 2000s, the cost of producing these was quite high and metrology methods were yet to catch up. Now, in the past few years, metrology and manufacturing methods have evolved to better support the advancement of freeform technology. High-resolution cameras, improved encoders, software algorithms, those all lead to what we're able to do now. So companies, including Spectrum Scientific, now offer a current state-of-the-art freeform optic in high volume with high fidelity and performance that in most cases is diffraction limited. As you know, nearly all technologies rely on precision optics. So naturally, freeform optics address many market needs as well, and they fit into nearly every technology sector for both high-tech and commercial applications. The advantages of freeform optics over conventional optics, such as increased aberration correction and optical volume reduction, can apply to a wide range of industries. Some commercial applications include LED lighting, where they are able to more efficiently distribute the light energy. In the automotive industry, nearly all headlight lamps and reflectors are a type of a freeform shape, and they've been doing freeforms for many years. Industrial applications, high power lasers for beam shaping, those are using freeform lenses. In life sciences, they want compact devices for point of care. In telecommunications, the designers are continually pushed and required to come up with more compact, optically efficient designs. One of the interesting applications for defense and aerospace I came across recently was aircraft wing optics. Those are pretty interesting. If you ever get a chance to look into those, it's really quite fascinating what they're able to produce. In the past, freeform optics were often too costly and too time-consuming to manufacture. So recent advancements in optical designing, manufacturing, and metrology are creating more opportunities to utilize freeforms in a wide range of industries and applications. So we've kind of grouped them into three here on this slide. We have non-imaging applications like LED lighting, laser beam shaping, illumination, light collection. We focus mostly on imaging optics here at Spectrum Scientific. Improvements in direct manufacturing methods such as diamond turning and MRF methods allow for effective production for low volume requirements of high precision imaging optics. Aerospace projects, R&D projects, and prototyping contracts will usually use these direct manufacturing methods. Now, high volume manufacturing technologies, including SSI's optical transfer process, allow for dozens or even hundreds of parts to be made each week while maintaining a high level of repeatable precision. So why are some companies choosing to go with freeform optics? I'm sure you already have many of your own ideas. I'll go through a few of the ones I know of. Clearly, fewer optics in the systems is a great advantage. When you can combine the function of two or more optical surfaces into one, that becomes quite powerful. And fewer lenses and mirrors in the system means less optical scatter. In some cases, fewer elements means reduced assembly time. And of course, fewer components lead to lower hardware costs, less inventory. Overall performance improvement is clearly one of the most common advantages and sought after reasons to go to freeforms. We've seen companies who've just improved one optic in an existing system, and suddenly they're getting diffraction limited performance or other performance improvements just by changing a single optic. Space applications benefit greatly when using freeforms because reduced mass and volume are key benefits for launch requirements. Bulky lens assemblies have been converted into off-axis mirror designs. The Center for Freeform Optics has a great example of this. If you go to their website, they were able to convert a large lens assembly into a few reflective mirrors and really decrease the size and maintain the performance. Another things you could do with freeforms is by going to a bigger numerical aperture, increase the étendue. So as the F number increases, it gets harder to control aberrations, but a freeform optic might be able to solve that for you. A great example of freeforms is the telescope in Hawaii. It's called the Scuba Telescope. It was redesigned with 9 freeform mirrors, and now they're able to examine the sky 1,000 times faster with a much larger field of view and with better signal-to-noise ratio than the original telescope. Like many optical systems, application environment and other system requirements will often determine the best manufacturing and measurement method. Each and every freeform project will be unique, so each manufacturing case needs to be treated separately. Some designers often ask, what are the limitations? When have we exceeded what can be manufactured? Basically, I think it's steep curves that are the most challenging, not just challenging to make and to measure. And we'll address that a little bit more in an upcoming metrology slide. So what does the designer need to provide to the manufacturer to be successful? As we stated earlier, the customer supplies a surface equation to the manufacturer, and we strongly suggest that both parties generate and compare SAG tables. This table is verified by the customer, and it becomes a reference table for a point cloud that will be generated by contact or non-contact probes or even interferometric data. In most cases, aligning a freeform is similar to aligning an off-axis A-sphere, where all 6 degrees of freedom must be precisely controlled. Therefore, the surfaces should have reference datums or alignment features that can be picked up by the machine operator and the end user. This is extremely important during manufacturing, and again, we're going to touch on this later because the fiducials and alignments are that important. So we'll come back to that. On this slide, we have 3 categories of manufacturing methods. It's generally understood that injection molding and nanoimprint lithography rely on direct manufacturing methods to produce the original optical surface. In molding and nanoimprint lithography, surfaces made by CNC machining, single-point diamond turning, or MRF techniques provide the top-level tooling which high-volume parts are made from. For less demanding applications, glass and plastic injection molding techniques are often used. But large volume of high specification surfaces, nanoimprint lithography will be the most precise while while minimizing batch-to-batch variation. Manufacturing freeforms, when you're manufacturing them directly, they're done one at a time. Unless it's a lenslet array or a set of micro lenses. Because for larger optics, you don't just gang them up on a spindle and grind and polish them all at one time. They're usually made one at a time. So as you can imagine, that requires many hours of grinding and polishing to produce a single part. So a machine can be tied up for a long time. And injection molding and replication type processes have the advantage of making a set of molds or tools that can be used to create dozens or hundreds of parts at a time. Also, for direct manufacturing methods, part-to-part and batch-to-batch variations are common, especially for high specification parts. Methods optimized for high volume production have reduced variability since each part is obtained from the same master mold. There are cost considerations for higher volume production scaling. When you're manufacturing originals, there's usually a setup fee, NRE tooling fee. They're typically a few $1,000s. For higher volume manufacturing methods, there's a higher upfront costs, and that kind of just makes sense when you think about it, because we're moving more parts through the production floor, so you have more carriers and fixtures to associate with all these parts being made. So the upfront tooling costs will be a little bit higher. So you need to consider, you also need to consider when you're doing high volume stuff, you've got to buy a few original freeforms anyway, just to start it off. So the cost of the original freeforms is still embedded in that cost of ramping up to higher volumes. So we move to the metrology side. Testing and measurements are taken by contact and non-contact methods. Besides mechanical dimensions, optical parameters usually include surface figure, roughness, and mid-spatial frequency. Of course, different applications require different levels of precision for each measurement parameter. For replication and molding processes, the master molds are measured to a very high level of detail. However, not all these measurements are always necessary during final production. Surface roughness and mid-spatial frequencies will typically remain constant during production. It's surface figure and cosmetic inspection that are commonly the parameters that are measured. And so for some customers, we measure those 100%. So some customers allow us to do batch-to-batch testing or AQL testing for a given batch size. And again, you might have recall I mentioned that for freeform surfaces, only a few microns or fringes of departure is required from a standard surface, so nanometer level metrology must be used. When using interferometry, if the slopes are too steep, the fringe density on the interferometer will exceed the pixel resolution. So it helps to have a high-resolution sensor. If you cannot resolve the fringes, you're going to have to move to a probing method, either contact or non-contact probing. Not long ago, CMM was a common method of measuring freeform surface. I recall even 10 or 12 years ago, I was in a shop, and that's how they're doing it. They're using the CMM to get a point cloud. And but however, the newest generation of contact and non-contact probes offer tremendous precision. Not long ago, or excuse me, fiducials, I need to get back to the fiducials again. Freeforms are more susceptible to alignment errors than conventional optics. Most aspheric surfaces can be measured with interferometry using first principle methods, where point sources and plane wave interferometry can be used to null the wavefront. Freeforms do not have this advantage. Therefore, fiducials and datums are critical for angular and linear coordinates. The manufacturer will use these for production and test, while the end user will rely on fiducials for system integration. That's the end of my portion of this webinar. I'd like to hand it to Merten for the next section. Thank you.
Thank you. Yes, hello everybody from my side as well. Thanks to Byron and David so far. Let me start with some words about Mahr first. Mahr is a family-owned company that is looking back on more than 150 years of history. We have approximately 2,000 colleagues working in subs in 18 countries worldwide, and Mahr is active in more than 60 countries. The main business is dimensional metrology. The company became well known for its handheld metrology like calipers or indicators, but is nowadays also developing and selling complex measurement machines for automotive industry and of course for the optical industry. The wide spectrum of products covers the measurement of a number of quality characteristics. Especially in optical manufacturing, measurement solutions are available for every process step in the production of optics. This ranges from 2D tactile profilometers for the correction of grinding processes up to non-contact point sensor systems and interferometers used for quality control during polishing. Okay, let's talk about freeforms. David already mentioned that fiducials play a special role when it comes to mounting, manufacturing, or measuring of freeform optics. And yeah, we can simply translate the word fiducial with reference. And here's a simple example that should give us a feeling of what a fiducial is. We have 4 pictures showing the very same wallpaper, and if I ask somebody which of the pictures has the correct orientation, you would probably say that you have no clue. But if we enlarge the picture section, so this little lamp becomes visible, we are able to answer the question because we know about the usual orientation of a lamp. We use this lamp as a fiducial in order to eliminate the freedom of rotation. And this is basically what the main function of fiducials are. They are required to reduce the degree of freedom. Reducing the degree of freedom becomes important when we measure optical surfaces, especially freeforms. In order to make the errors of the surface visible, we subtract the nominal shape from the measured data. To do this, the data are fitted into the nominal shape in order to minimize the RMS value of the differential surface, which is the result. In the 3D measurement, we have 3 translational and 3 rotational freedoms. The differential topography is then sent back to the processing machine in order to eliminate the residual deviations, for example, improve the PV value and bring it within the specification. If the algorithm for fitting has too many freedoms, it is possible that a wrong result is computed, like in this example. In this case, the differential topography has the same RMS value like the previous one, but it is obvious that using this topography for correction will aggravate the deviation of the surface instead of improving it. So in order to improve the quality of the fit, it is necessary to lock freedoms. In this case, it would help to lock the rotation around the Z-axis. So using mechanical fiducials require a proper metrology equipment. This is where I want to introduce the Marform MFU200 aspheric. This machine is equipped with two sensor systems, which are an interferometric point sensor and an inductive tactile system. Besides this, the system has several measuring and position axes. One of these is the high accurate rotation axis that is used to spin the sample in order to record measurement data along concentric circles. On top of this rotational axis, we can find a motorized tip-tilt stage that can be used for automatic centration and alignment of the optic. So if we take a closer look at the sensor head, we see the tactile measurement system can be rotated around 360 degrees. That makes it possible to swivel the optical sensor, which is now active, and change between it and the tactile sensor, which is now at the bottom. Yeah. This is possible at any time without moving or unmounting any parts. Let's talk about some examples. The first one I would like to show is actually no freeform, but it explains the usage of fiducials very well. This is an aspheric mold used for pressing of aspheric lenses. And this part is diamond turned, so we conducted 2D measurement, assuming that the surface errors are rotationally symmetric. So if we now fit the measured data into the nominal shape, we have 3 degrees, 3 freedoms, 2 lateral, and 1 rotational. The problem could be in this case that the asphericity of the optic is very low, so the rotational freedom will cause an error because the algorithm cannot converge. So we need to get rid of this rotational freedom, and we do this by untilting the part using the plane of surface at the top. Therefore, we increase the scanning length to have sections of the plane of surface in the profile. These sections can now be used for additional alignment of the data in the software, and the rotational freedom will be locked and the correct result can be found. The second example I would like to show is a Tauric lens. Just as a reminder, a Tauric lens is a lens that has 2 different radii of curvature along the X and the Y direction. We can imagine a Tauric like the slice of a donut. On this optic, a 3D measurement will be conducted. That means we have 6 freedoms and we are going to eliminate 3 of them. Therefore, we use the outer boundaries as mechanical fiducials of the part. First, we eliminate the rotation around Z, which is also called C. Therefore, a tactile scan is done at the front side of the element, and the resulting line delivers now information about the current rotational misalignment angle theta, which is then compensated by rotating the part around this angle in the opposite direction. Next alignment procedure will take care about the centration of the part on using the machine, using the motorized stage of the machine. This centration will be done on the outer boundaries as well, contacting each side once and detect the position of the optical element. So by knowing the position of the four sides side surfaces, the part can be centered. After the alignment, the actual measurement of the optical surface is done by measuring 35 circular traces and segments using the interferometric point sensor. This is done by rotating the part using the Z-axis, as we can see in this video. The machine operates in active tracking mode here. That means that the vertical axis moves the sensor head up and down in order to follow the shape of the surface. Okay, evaluation. From the 6 freedoms that initially existed, we eliminated 3, which allows us to compute the correct differential profile now and make sure and make the surface deviation visible. Okay, our last example for today is an off-axis toroid. This is a surface that is created by rotating an aspheric profile around an axis. We can imagine the resulting object as a Chinese lantern. From this, we imaginary cut out a piece of the aspheric axis, and the resulting optical element has now a circular form in one direction and an aspheric form in the other direction. If we take a look at the backside of this part, we can see there are 2 linear edges that are used for the mounting of the component in the final optical assembly. We will use these edges as fiducials now, and to mount the mirror during the measurement, a special holder is used. This one is equipped with 3 ruby balls, 1, 2, and 3, as well as with a belt stop on the left side. These elements and the upper linear edge on the part itself are now used to eliminate 5 freedoms. Okay, so we can basically say that we reduce the freedom X with ball 2 or 3, and the edge of the part that is eliminated by ball 1, 2, and 3. Ball 2 and 3 and the edge determine the rotation around X. Ball 2 or 3 and ball 1 determine the rotation around Y, which is also called B. And ball 2 or 3 and the edge determine the rotation around Z, which is also called C. So the position along the Y-axis is fixed by the bed stop. So this is the only position that is not determined by the balls. We see that it is crucial to know the exact position of the 3 balls, and this is necessary to be able to transform the coordinate system of the nominal topography into the machine coordinate system. This becomes possible by determination of the zenith positions of each of the 3 balls, which is done using our optical sensor. And after this is done, we can measure the surface of the mirror again with concentric circles. Yeah. So 5 freedoms have been eliminated in order to evaluate the measurement. Now we allow the fit algorithm only to shift the measured data along the y direction to compute the resulting differential topography. And the previously measured positions of the Ruby balls are used to shift the coordinate system of the nominal topography into the machine's coordinate system. The resulting differential topography contains now all deviations of the optical surface itself and the deviation caused by a misplacement of the surface with respect to the mounting edge. This resulting differential topography can now be transferred back to the processing machine for the correction process. And the already mentioned inseparability of the deviations is not important, since the resulting error refers to the mounting interface of the part, which is the final decisive criterion that has to be fulfilled. The optical surface is manufactured correctly with respect to the final mounting. Okay, that's from my side. I would like to hand it back to Byron Siebold now.
Thanks so much, Merten. So again, we really appreciate everybody's time. I hope that you found this webinar to be useful. Before we get into Q&A, I would like to go over some general announcements. As many of you know, Photonics West 2019 is just around the corner. So starting 10 a.m. Tuesday of next week. And Spectrum Scientific will be at booth 1972. And they are, I think, almost directly beside us. And we, Mahr Incorporated, will be at booth 1861. At the Mahr booth, we have several activities going on. We'll be doing a live presentation and demo for Freeform 3D metrology each day of Photonics West, particularly over example number 3. So example 3 in this particular webinar today is what we'll be actually demonstrating and going over the presentation again. And I know there were some issues with some of the animation within the webinar today, so you guys will be emailed links so you can download the video and watch over again. We did record this webinar today, but nevertheless, this live presentation and demo at the Mahr booth, and that's again booth 1861, on Tuesday from 2 to 3, Wednesday 2 to 3, and on Thursday from 1 to 2 p.m. We'll also have a wireless precision gauge for optical applications demonstration taking place as well. And there's a chance each day to enter and win free wireless calipers. So everybody likes free stuff. So if you get an opportunity to come by and see the live demonstration on Freeform 3D metrology, also swing by and check out the wireless hand tools for optical applications and try to win a free wireless calipers. So anyways, that's all for the announcements. Again, thank you very much for attending, and we'll jump to Q&A. So let's see what we have first for questions. One second, everybody bear with me. There's quite a few. So let's see. How is the metrology verified?
Well, for some kind of parts, there are possibilities to check against other metrology concepts, like interferometry. Yeah, basically.
There's some traceability with some other artifacts and through conventional interferometry and things like this in some cases.
Yeah, as long as this is possible.
Yeah.
Otherwise, it's always like Dave mentioned it. always possible to check against coordinate measurement machines.
Okay.
As the most versatile measurement machines in general.
Well, and I think also too, Merten, is that the question of how is the metrology verified can even go into a deeper conversation as well.
Yeah.
How exactly how are you describing the surface, as David mentioned in the first part of the webinar, et cetera, et cetera.
Yeah.
For the person that asked that, I won't call out anybody's name specifically, but thank you for the question, and I think we'd be happy to discuss that offline a little bit deeper. It really depends on the geometry of the shape of that particular optic, and in terms of how it's being verified or certified in terms of the measurement results.
Yeah, and it's always important to know that different metrology will make different kinds of errors visible. So you cannot see all kinds of errors like high spatial frequency or mid spatial frequency with interferometers, for example. So it's always the question what I'm looking for.
Yeah.
What is the most crucial error I have on my optic?
So the follow-up question with this from the same person is, so to be convincing, parts should be measured using two techniques.
Definitely.
What was used to compare with the MFU to convince you that it was accurate and precise?
If I could step in, Byron and Merten, we've had projects where the MFU measured it, and we subsequently measured the same part on interferometer and found the MFU is a very close match within a couple nanometers.
And David, would you agree that it sort of goes back to, it really depends on the geometry and how severe the slopes are and things for us to be able to go back to conventional metrology techniques to do that verification?
Yeah, I mean, the point is a great point. If you can get several measurements on one part, you feel much more confident. We don't always have the luxury of having multiple tools to measure it. And especially if it's beyond what an interferometer can measure, you've got contact or non-contact probes that need to be used. So that's where it tails back to that first question: how do you know how accurate your measurement is? So far, what I've seen in the metrology world is the accuracies are quite good. With 10 nanometers or so, I mean that's fantastic. And you see it, at Photonics West, you'll see at the Mahr booth, quite impressive specifications, and I've learned to trust them at this point, as long as the user's doing it right, and that's just our experience with it.
Thank you, David.
Thank you.
So I'm going to move on to some other questions, and just for time purposes, I may not get to every question, but we'll definitely have a list of those. So we'll be reaching out individually to have a side discussion as well. So forgive me if I skip your question. So the next question is, I was wondering if you could talk a bit regarding tilted wave interferometry for freeform, its advantages, disadvantages, where it's headed, etc. So I will answer this right now and say that we will be following up with a webinar on tilted wave interferometry. I'll be a little bit careful about when we plan on having this instrument in one of the upcoming trade shows in the future. So I'm sort of answering but skipping around it a little bit because hopefully we'll be able to answer that question more in depth with an upcoming webinar, probably around second quarter, third quarter of this year. But nevertheless, we'll talk offline with the person that wrote that question a little bit more in detail. And also, I think there was a follow-up. Will we be at the Baltimore show in April? We don't have plans this year to attend that show. So the next question is, what is the accuracy or uncertainty of the non-contact optical probe And what is the maximum diameter you can measure?
We specify a accuracy of the optical probe within plus minus 50 nanometer, and the maximum diameter that can be measured on the MFU is, depending on the probe geometry, up to 200 millimeters.
Thank you, Martin. Let's see. Can you please give some thumb rules regarding the surface slopes? Can you please give some thumb rules regarding the surface slopes that can and cannot be produced? So I think this is a question for you, David.
Yeah, I wish I could just give an angular limit, but that's going to depend on your interferometer. Some of our interferometers don't have the high resolution cameras, and there's always going to be a limit. So it's a mathematical question where each interferometer is going to have its own limitation. It'd be nice to work up an equation so everyone can figure that out, but it's probably highly dependent on the setup in front of the interferometer as well.
In terms of like producing like high surface slopes, what is in your experience, David? What can and can't be produced? Maybe using the replication process.
Wow.
I mean, it might be a loaded question, but
so we primarily produce reflective mirrors, reflective optics, and we've done F1 type mirrors in the replication process. As far as measuring those is pretty tricky, but that's just standard aspheric type stuff. We haven't approached any freeforms with that kind of a F number. I think if I say F1, most of the audience is satisfied with that.
Yeah. Okay. So the next question is: would you see more use of these optics in the production of the products, or in the production in the molds or tooling?
Can you repeat the question? What was that?
Would you see more use of these types of optics, I'm assuming freeforms, in the production of products or in the production in molds or tooling?
Well, they go hand in hand, don't they? Don't we need the tools to produce the products? So we get requests every week for these types of things. And
I can imagine that the question meant something: would you see more use of these metrology in the production of products or the production of the molds?
Yeah.
I don't know if this is what is meant here, and it really depends on the process,
Right.
I guess.
But I think to David's end, David, I think you have a good point. Is that, I mean, they do sort of go hand in hand, and I guess you could read it the other way as well, right?
Definitely.
Yeah. The interpretation. Moving on, let's see. So there was a question at Photonics West: will the MFU be set up and functional? Will you have some of these freeforms there as part of the measurement? I hope I was clear, and I apologize if I was not. We will be holding the live presentation and demo of the MFU 200, and example 3, which was presented in the technical portion of the webinar. That is the sample we will be measuring at the trade show. So yes, the MFU will be there and be functional. So please do come by to check it out. Let's see. Next question: could you please elaborate on the plus or minus 50 nanometers you mentioned regarding the MFU? Is that the accuracy or precision, and how do you quantify that?
This is the accuracy is meant here, and we quantify it on, okay, this value was quantified on reference A-spheres. We have made them produced for this special purpose, and they were measured with a interferometer. So the plus minus 50 nanometer are just the accuracy of how these values we got from our measurement are matching with the reference measurement. So this is the only way how you can, but there is no real way how to trace back an A-sphere or a freeform. So this is the only way we could think of, that we just compare the measurement to established other measurement metrology in aspheric production.
Okay. Next question. And we got about 2 more minutes, but we'll field a few more questions. What kind of surface quality is necessary for measurements with the non-contact probe? Can it also measure ground surfaces?
Yeah, that's a good question. Of course, the optical metrology always requires a certain rate of reflectivity. So scattering surfaces are not able to be measured. But it can be said that since the MFU combines an optical and a tactile measurement system, it is also possible to just plug in a tactile probe, which then is able to measure ground surfaces as well.
Yeah. So it's
with a lower accuracy.
Yeah. So basically, the dual probe on the HV axis allows you for being able to measure a ground surface. Yeah, or you can replace the whole probe. Yeah.
And insert a tactical probe with a diamond probe tip.
And so how does when you remove the dual probe, and that's kinematic mount?
It's a magnetic mount.
Yeah. Okay. And let's see. Well, that is the end of the questions. So everyone, again, thank you very much for joining. Thank you, David. Thank you, Merten. We really appreciate everybody's time and effort that was put into this, and we hope to see you all at Photonics West. Please flood our booth and also flood Spectrum Scientific's booth with questions. We very much would appreciate this.
And thank you very much, Byron, for guiding us through this webinar.
Yeah, absolutely.
Thank you,
all right.
Byron.
Yeah, thanks, everyone. Have a great day.